More function visualizations. So let's say you have a function that's got a single input, t, and then it outputs a vector. And the vector is going to depend on t, so the x component will be t times the cosine of t, and then the y component will be t times the sine of t. This is what's called a parametric function. And I should maybe say one parameter parametric function. One parameter. And parameter is just kind of a fancy word for input. Parameter. So in this case, t is our single parameter. And what makes it a parametric function is that we think about it as drawing a curve and its output is multidimensional. So you might think when you visualize something like this, it's got, a single input and it's got a two-dimensional output. Let's graph it, put those three numbers together and plot them. But what turns out to be even better is to look just in the output space. So in this case, the output space is two-dimensional, so I'll go ahead and draw a coordinate plane here. And let's just evaluate this function at a couple different points and see what it looks like, okay? So maybe the easiest place to evaluate it would be 0. So f of 0 is equal to, and then in both cases it'll be 0 times something, so 0 times cosine of 0 is just 0, and then 0 times sine of 0 is also just 0. So that input corresponds to the output. You could think of it as a vector that's infinitely small, or just the point at the origin, however you want to go about it. So let's take a different point, just to see what else could happen. And I'm going to choose pi halves. Of course, the reason I'm choosing pi halves of all numbers is that it's something I know how to take the sine and the cosine of. So t is pi halves, cosine of pi halves. And you start thinking, okay, what's the cosine of pi halves? What's the sine of pi halves? And maybe you go off and draw a little unit circle while you're writing things out. Whoops. This is the problem with talking while writing. Sine of pi halves. And it's, if you go off and scribble that little unit circle, and you say pi halves is going to bring us a quarter of the way around over here. And cosine of pi halves is measuring the x component of that, so that just cancels out to 0. And then sine of pi halves is the y component of that, so that ends up equaling 1. Which means that the vector as a whole is going to be 0 for the x component and then pi halves for the y component. And what that would look like, the y component of pi halves is about 1.7 up there, and there's no x component, so you might get a vector like this. And if you imagine doing this at all the different input points, you might get a bunch of different vectors off doing different things. And if you were to draw it, you don't want to just draw the arrows themselves, because that'll clutter things up a whole bunch. So we just want to trace the points that correspond to the output, the tips of each vector. And what I'll do here, I'll show a little animation. Let me just clear the board a bit. An animation where I'll let t range between 0 and 10. So let's write that down. So the value t is going to start at 0, and then it's going to go to 10, and we'll just see what vectors does that output, and what curve does the tip of that vector trace out. So here it goes, all of the values just kind of ranging 0 to 10, and you end up getting this spiral shape. And you can maybe think about why this cosine of t, sine of t, scaled by the value t itself would give you this spiral. But what it means is that when you, we saw that 0 goes here. Evidently, it's the case that 10 outputs here. And a disadvantage of drawing things like this, you're not quite sure of what the interim values are. You could kind of guess maybe 1 goes somewhere here, 2 goes somewhere here, and you're kind of hoping that they're evenly spaced as you move along. But you don't get that information. You lose the input information. You get the shape of the curve, and if you just want, an analytical way of describing curves, you find some parametric function that does it, and you don't really care about the rate. But just to show where it might matter, I'll animate the same thing again, another function that draws the same curve, but it starts going really quickly, and then it slows down as you go on. So that function is not quite the t cosine t, t sine of t, I originally had written. And in fact, it would mean that, let's just erase these guys. When it starts slowly, you can interpret that as saying, okay, maybe, well, actually it started quickly, didn't it? So 1 would be really far off here, and then 2, it could have zipped along here, and then 3, still going really fast. And then maybe by the time you get to the end, it's just going very slowly, just kind of 7 is here, 8 is here, and it's hardly making any progress before it gets to 10. So you can have 2 different functions draw the same curve. And the fancy word here is parameterize. So functions will parameterize a curve if when you draw just in the output space, you get that curve. And in the next video, I'll show how you can have functions with a 2-dimensional input and a 3-dimensional output draw surfaces in 3-dimensional space.